One of the first topics that we encounter in calculus is limits. So I'm going to give you a little introduction to that right now. First thing I want to give you is the notation of limits. So you will see a limit written like this. Usually c is a number, and f of x is a function, and n is also a number. So you'll see this notation. Basically what this says is the limit of f of x as x approaches c equals n. So basically what this is you'll have a function, and this n is going to be the value of the function, which is the y value, when x gets really, really, really close to c. And oftentimes, it will be just the y value when you evaluate it with c. So let's do some examples. So I have 3 examples here. Many limits are going to be actually easier than you would think. You just have to substitute in this x value for the x in the function that you have. So for this one, you get 6 times 2 squared, which gives you 6 times 4, or 24. That's the answer for that one. You can do the same thing for number 5. If you substitute in 5 for x, you end up getting 42. So those two are pretty nice. You just substitute in. The problem comes when you have something like 3. So if you substitute in 2 for x, you are going to get a value of 0 over 0. That, unfortunately, is not going to be an effective answer, not a correct answer. So I'll show you what we can do for this problem. And there are actually several ways to solve this. I'm going to start by graphing it, just because I think having a visual is really helpful for this type of thing. So if you graph, so let's do it by graphing. That's our first method. So if you graph this, this is a rational function. We have x minus 2 times x plus 2 over x minus 2 if we factor it out. When you factor that, if you remember with rational functions, when you have a factor that cancels out, that means that you have a hole in your graph, and that hole is going to be at x equals 2. So let's graph this now. So this is going to be the same as the graph of f of x equals x plus 2, but with that hole at 2. So if we draw that, our y-intercept's at 2, and our slope is 1. So this graph looks like this until we get to x equals 2, where we have that hole in the graph. So the way that you can find the limit here, the limit, unfortunately, is not going to be the value of f of 2, but if you notice, as we're approaching 2 from both the left side and from the right side, we get really, really, really close to y equals 4. So actually, the limit of this function as x approaches 2 is going to be, I'm just going to write this as f of x, 4. So that is one way to evaluate this. Being able to look at the graph and do that is really, really nice. You might not always have your function defined at that point, but you often will be able to find the limit. Okay, I'm going to show you the second way to do this problem. So the second way to solve this problem is by factoring. And you might notice that we already factored it. I do want you to notice as I'm doing this, by the way, that until I actually evaluate this function, I am going to keep the limit notation here, so don't forget to write that down. So if we factor it, then we cancel this out. We actually did that already. This is going to be equivalent to the limit as x approaches 2 of x plus 2 Now you can actually go ahead and use what we did before, which is substituting that value of 2 in. When you do that, you end up getting 2 plus 2, which is equal to 4, the same thing that we found using the graphing method. So here's a few piecewise functions for you. You are welcome to graph these, and in fact I am going to require that you do graph a few of these ones. However, you can also evaluate them sometimes without graphing. I think having a picture though is usually very helpful. However, for number 4, you don't actually need to graph that one. It's probably just as easy to not graph it. So we are going to be finding the limit of this function as x approaches 0. You'll notice that I have 2 parts of the piecewise graph. This one right here is when x equals 0 falls into that place. So actually you just evaluate this one by substituting in 0. Those are not usually the type of problems that you're going to get in a calculus class. You're usually going to get stuff more like 5, and then 6 is going to be on the next slide. So for number 5, I am given this piecewise function. I'll go ahead and draw it for you so you can see what that looks like. So this is what that piecewise graph looks like. You'll notice the line's not perfectly straight, but hopefully you get the picture. You'll notice that there is a hole at x equals 0. In addition to that hole at x equals 0, I have an extra point at 0, 4. So for this type of function, you have to look at where the graph is approaching from both sides, not necessarily where the function is defined. So if I'm going along from the left, I end up right there. If I'm going along from the right, I end up there. We're going to ignore that little point discontinuity. Our value of our limit is actually going to be at 1. Be really, really, really careful on that. That 4 is just an extra point. We don't need that to find our limit. So here's another piecewise function. You're welcome to graph this one on your own. I think it'll be really helpful if you do actually graph it. So if you draw this graph, you might notice that if I go from the right-hand side, I end up getting my y value at -1. If I go from the left-hand side, my y value approaches 1. And you might say, well, the function is defined at -1, so isn't that the answer? The answer to that actually is no. The limit of this function, we say that the limit does not exist. You need to have your function approaching the same y value from both sides. So we say the limit does not exist. And we often will abbreviate that as DNE. So you can just write that when you have a test or a quiz. So for this last problem, you'll notice I didn't actually even give you an equation. I just gave you the graph. That often happens with these problems. So take a look at this graph. I have a function, and the function is not defined at x equals 0. I want you to take a guess and see if you can guess what the answer is. So if you said 3, very good. First of all, the limit does exist. The reason it exists is because as it approaches 0, you do have the graph approaching 0 from both sides at the same y value, and that y value is 3. So just keep in mind that if you have a hole in your graph, you still can have a limit that exists as long as it is approaching the same y value from both sides.